Hello everybody. Welcome. Thank you for joining us today online. You are part of the more than 180 people worldwide who have registered to this webcast, powered by Yole Développement, System Plus Consulting, and PZO. It is entitled Thermal Imaging, the Rise of Fever Detection and the Global Market Application and Evolution. How today's session will last about 1 hour with 45 minutes presentation and about 15 minutes of Q&A session. My name is Faisal El-Kamasi and I'm a global sales support and coordinator for Yole Développement. To shortly introduce you, Yole Développement, Yole Dev, we are part of the Yole Group of Companies which providing marketing, technology and strategy consulting, media in addition to corporate finance services. We support industrial companies, investors and R&D organizations worldwide to help them understand markets and follow technology trends to develop their business. Back to this event. Before we get started, let me give you some basic information about this online event. During all the webcast, you can ask questions using the button Ask a Question at the bottom of your screen. Question will be answered at the end of the session. We will answer as many questions as we can today, and remaining questions will be answered through emails. Concerning the materials, please note that the presentations are already available and downloadable in the resources section of the platform. Within 24 hours, you will receive an email with a link to the recorded webcast session. I'm pleased to welcome today our three keynote speakers. Dimitrios Damianos, Technology and Market Analysis, Imaging and MEMS at Yole Développement, Sylvain Halero, Senior Technology and Cost Analysis at System Plus Consulting, and Olivier Andrieux, Innovation Leader and System Architect at PZO. They join forces to provide you a better understanding of today's thermal imaging market and its evolution. So now, we're going to start with the first presentation of Dimitrios. So Dimitrios, the floor is yours.
Hello, everyone. I hope you can hear me well and maybe see me well. I don't know, I have activated my webcam. So welcome today. Thanks, Faisal, for the introduction. So from my side, I will speak about the global thermal camera market and maybe focus slightly on the fever detection hype that we saw this year, as you already know, those of you that are in the domain. So actually, in Yole, we monitor the infrared technologies, notably in the infrared spectrum, which is very large. We focus at the long-wave infrared. And there are various types of sensors, actually, that monitor these wavelengths, these various infrared wavelengths. So they are mostly categorized in two technologies. The cooled ones, where the output signal of the sensor is proportional to the number of absorbed photons, but they need the cryogenic cooler in order to function. And we have the uncooled technology. So these are sensors that work by detecting thermal radiation and absorb the infrared wavelength, which causes change in the temperature of the device. So this is converted to an electrical signal. And in that case, there is no cryocooler that is needed here. So in Yole, we focus actually on the long-wave infrared and the uncooled based sensors, notably pyroelectric and thermopiles, which we consider as thermal detectors, which means sensors that typically have few elements, few pixels, and they can do some basic functionalities such as simple detection or sensing. And then we have microbolometers, which we call thermal imagers, actually. So these have the capability to convert infrared radiation into visible image. Next, I'll show you the applications that we cover in Yole. From the thermal detector side, we have commercial applications like typical motion detection for security, for energy savings, like lighting, etc. Simple temperature measurement, like contactless thermometers and guns. Spectroscopy applications with typical linear arrays, gas and fire detection, and smart buildings like HVAC, savings, heating, ventilation, air control, actually, and other people counting or basic functionalities for these big application. Thermal imagers, on the other side, they have both commercial and military applications. The military applications, which are, let's say, more historical, include thermal weapon sights, soldier vision, and other applications like missile seekers, like driver vision enhancement, remote weapon stations, etc. And commercial applications, which have been developed during the past, let's say, 20 years or so, including thermography, surveillance, automotive, firefighting, marine or maritime, personal vision systems, ruggedized smartphones, plug-in for smartphones, and other commercial, which we consider mostly drones, let's say. So this is the focus, actually, of this webinar in the thermal imager side, and of course the thermal cameras, but is also this slight focus on the elevated body temperature, the elevated skin temperature hype of 2020. So just to say here that the search trends, the general public actually became well aware of infrared technologies, because we saw that there are various such trends that spiked in May that are relevant actually to the body, the fever detection, to the human body temperature, because actually this was the first of the main symptoms of COVID-19. So the general public had raised awareness, and with that came the interest in infrared thermometers, but also thermal cameras or fever cameras. Now, actually, there was a lot of contradicting information out there in the beginning about, let's say, where to measure the temperature, about the system requirements, etc. So there are various academic studies actually showing a correlation between internal core temperature and the facial skin temperature. And the best way to measure is typically from the lacrimal ducts, the tear ducts between at the eyes. So this is, let's say, the most representative temperature of the inner body. And actually, there are two ways to measure the temperature. One initially is the infrared thermometer, which typically has a single spot, a single measurement spot, and is taken typically from the forehead. And the cameras, the thermal cameras, are allow for capturing a bigger area because they have many pixels and higher resolution. So they allow for scanning and isolating the area, the lacrimal duct that I said earlier. So this is very important, let's say, to have some information about the body temperature. So actually, something else that we should take into account is that the skin is thin in this area. So this decreases the insulating effect. So this is one of the critical parameters that affect the measurement. And it's also to be taken into account that there is a difference between the facial skin temperature and the ambient air temperature. So there should be some software there that takes into account to correct this offset in real time, but also very important is factory calibration, but also in real time use a black body must be used, the black body source, in order to have a stable source at the range of the human body temperature between 30 and 45 degrees. Now, some important criteria when measuring the temperature of humans is there are some criteria that must be taken actually into account, and those can be either technical or use case. So first, the measurement must be radiometric, because non-radiometric cameras do not have the needed accuracy, so they can have a risk of false positive. The next is a temperature accuracy that must be at 0.5 degrees or below that in order to avoid false negatives. And for that, as I said, there is a possibility to use at the measurement site some black body source. Also, the resolution is important, because having a high resolution, this allows for capturing minuscule details and isolating the various regions of the face, as I said, the tear ducts. Finally, on the use cases, while typically it's known that it has been very publicized, let's say, marketed, that thermal cameras can scan like multiple persons at once. This is not the most ideal situation, because people that are at various distances, they will be out of focus of thermal cameras. So this will not give, let's say, the best temperature measurement for everyone. So ideally, one person at a time should be scanned at the correct distance, at a fixed distance every time, and the focus at the tear duct should be done. And finally, environmental conditions are also important, because they could alter the measurement. For example, when we are outside in the cold or in the heat, if it's summer, I don't know, and we have this affects our skin temperature. So when we measure directly, we're using a thermal camera, this will give some false measurements. So ideally, the people that are supposed to get measured should wait in a controlled temperature place. So just to give you an overview of the thermal camera market in general. So as I said, these are the applications that I explained earlier very briefly that we monitor in Yole. And in 2019, the market amounted to almost $4.5 billion. Of course, the most important was defense, the defense military applications. So what we expect actually here in 2020 is the thermography market to spike, to surge actually unsustainably. And this originates from the fact that fever cameras, EBT or EST cameras, however you like to call them, they got a lot of interest. They got adopted at various critical infrastructure like airports, schools, businesses, etc., because they allowed actually the return, let's say, to some normality and to control actually the temperature of the people. So actually from 2021 and later, we cannot say if it will be, let's say, a COVID-inspired year. I mean, there could be maybe even a third wave. We're currently at the second wave, let's say, and maybe a third wave could exist if the vaccines are not massively maybe available. So maybe some interest could be regained around this technology. Why I'm saying this? Because simply all of these interest and all of these systems were initially sold at the period between, let's say, February, March, and July. And after that, all of the manufacturers have seen a decrease of the interest and of the orders around this system. So let's say going back to normal. And what is not known is next year what will happen. From the Yole side, we think that the demand will go back to normal. However, a significant sub-segment will be created in the thermography market, which we call this EBT or EST segment, as more businesses will be more interested, let's say, and other infrastructure will be more interested around this technology and use it in order to screen for people before when they're going to their building to their work or to the school or whatever, because this will allow actually to avoid febrile people entering and avoid cross-contamination, which would translate eventually to some let's say, decrease the number of people taking sick leave, for example, and this could be something interesting, let's say, for the businesses. Of course, it won't be at the same levels as this year, but it will be an important and significant sub-segment getting created there. Of course, we have more detail on that in our report in Yole. Of course, I cannot give all the details here. The time is limited. So just a few comments maybe about the other markets. Okay, so in 2025, we expect the market to grow up to $7.5 billion. The growth will be driven mainly by defense, the defense market, because we see an increased interest in infrared technologies, and long-wave infrared is getting more and more combined with other technologies like shortwave infrared, and it's a good, let's say, add-on for thermal weapon sights. Maybe the time is limited, so I cannot maybe comment on all of that. So I will go on to the trends that we are seeing actually in the main trends that we can mention here. One part is the automotive. That there is thermal imagers that are getting adopted, let's say, in the automotive for two main applications. One is the pure ADAS, or autonomous vehicle application. So on the ADAS side, safety is thermal imagers increase the safety by improving actually the automatic emergency braking functionality, but it's also can be used in cabin monitoring for the passengers in order to sense their activity. So there's already a product there from Valeo called Smart Cocoon. And on the other side, it can help drivers see at low light levels. So this is the pure thermal night vision. Also, we see a lot of interest in the drones, drone industry, a lot of companies that are integrating some thermal imager payload on their drones. So this is more on the commercial, let's say more professional side, but it's really an interest there. And also FLIR has released, I think the last couple of months, the last few months, two products dedicated on the drones, on the drone market. Actually, there is... okay, there was a bug there. So drones and also in general unmanned and autonomous systems are everywhere in the military ecosystem. There is in every, let's say, operational domain, there are these various, let's say, unmanned systems that push for better lethality and survivability, which in turn drives the framework for the situational awareness and the ISR, which leads in turn to adoption of these various systems in these various domains. So actually thermal imaging has clear place in such systems, which brings this extra added value. And thermal imaging is needed for increasing situational awareness. Let me go by quickly. I don't have much time, I think. So again, we are seeing, yes, this move to AI. Many fever detection camera manufacturers claim that they have AI. In general, we don't think that it's the best solution to show the AI, but the AI for thermal imaging exists in the military, like avionics pods, for example, or surveillance. For some perimeter or security detection, and with the good choices on the hardware and the software, it could be used in the future in other applications such as transport and medical diagnosis, and of course other applications. So this we show here the thermal imager manufacturers map. So these are the main players at the imager level. We don't show the whole here, the whole camera supply chain, because it's very complicated and spread worldwide. But this is who is in the domain and who you should know. I'll go by quickly and just say why I'm showing this map. It's simply to tell that during this year, due to this fever detection hype, we saw actually the thermal imager manufacturers from China getting a big, let's say, a share of the pie. Of course, here we saw the market share of the various manufacturers in units. And what we saw is that, as I said, the Chinese getting an important place there, ramping up their production, addressing their market domestically. And we're just wondering what will be the implications for the years to come. We're wondering if it's possible that they will become, let's say, the leaders, but of course, time will tell only. So the implications are actually for the years to come, and the next step is that right now these kind of players have increased production capacities. So possibly in the next years they won't know what to do with that. So they have to align their strategy and see if from the next year onward they will address traditional applications and push back traditional applications like thermography or surveillance by using their existing sales channels, or move into new untapped markets, which are, let's say, higher volume, maybe more on the consumer side, like smart homes, smartphones, drones, or whatever, or even industrial, like smart buildings. So again, this is something that we need to see, that we will need to see next year. So this was a small overview. I think I spoke quickly. There were a lot of things to say. We have, of course, more detail in our reports. And if you have any questions, feel free to ask at the end of this webinar. I'll give back the mic to Faisal. Thanks.
Thank you very much, Dimitrios, for your very interesting presentation. Yes, as Dimitrios said, once again, do not hesitate to ask questions for the Q&A session at the end of the webcast. So now let's continue our presentation with Sylvain Alero from System Plus Consulting. Over to you, Sylvain.
Better like this.
Yes, better like this, yes.
Hey everyone, I'm Sylvain Alero, cost engineer at System Plus Consulting. I'm in charge of thermal imaging, MEMS, and photonics component. And I'll present now the last result of the new analysis for the thermal imaging on microbolometers component. At System Plus Consulting, you work on the physical component, you perform physical analysis of the component in your internal laboratory, and after you perform the physical technical analysis to try to recreate the process, the manufacturing process of the component, and you have after the internal software to calculate the cost of the component. All the physical analysis are performed internal, and the software, the cost software are internal equally. For this presentation, I've made a review of 4 thermal imager with one on FLIR, the Lepton 3 module of FLIR, module of Zik Thermal with Rayton microbolometers, the GuideIR infrared module manufactured with O-film for the packaging part, and the Iray T3S smartphone camera. This is the last camera that has been studied by a PZO for the physical analysis of the performance of the component. The first, it's a FLIR. It's a leader for the thermography equipment. And they are the first equally to launch in the market a very few small module developed for the smartphone or a few very small thermal equipment. The camera is very small. We have a small definition with only 100, 600, 60 by 120 pixel low resolution with a 12 micrometer for the pixel, and we have a very small volume for the module. This module has been launched in 2014, and you can see here a cross-section of the module. The module is very small, that can be directly integrated in the smartphone or tablet. You can see at the here the microbolometer, the main component of the system, with a wafer level package. You can see here the window. And other specific technology developed by FLIR. It's the system integrates two lenses in silicon. It's the first company that use a silicon lens for thermal imaging and not chalcogenide or germanium lens. You can see here very specific lens manufactured with on silicon wafer with a specific technology to offer laser dicing to create the lens. This technology is very interesting because the silicon is very cheap and is very easy to obtain very large volume with this type of silicon lens. You have here some estimation for the characteristic of the lens, with possible to manufacture 1014 400 lens per wafer. For the microbolometer, it's a specific microbolometer with a low pixel resolution, but they use the same technology you have already seen for another more industrial or more high capacity microbolometer from FLIR. You have also the last generation of 12 micrometers pixel, and the low definition and the small pixel allow to have a very small die of only 21 square millimeters. For this slide, you can see the breakdown for this component, with the sensor for 30%, the lens module, the assembly, the yield, and the test cost, and the cost for the ASIC, because there are an ASIC in the module to make the first treatment for the picture. The estimate cost for the component is close to $20. That is only a cost without the gross margin of FLIR. The second module is module from SIG Thermal on Rayton for the microbolometers. The second American company that launched a specific component microbolometer on module for a smartphone. You can see here the module you can plug on the smartphone with a USB connector. This module has been launched in the market in 2014 for a price of $250. Yes. You can see here for the lens, they use only one lens in a chalcogenide lens material. With you can see here the shutter the electronic board, and the microbolometer is under the lens here. For the microbolometer from Iton, there are also a wafer level package with the ASIC and microbolometer die and the cap above. You can see here the ceiling, the cross section with the ceiling with a gold tin solder. For the die, the number of pixels is more important, with 3 times the number of pixels from the FLIR. And but for the pixels has the same pitch of 12 micrometers. You can see here some picture from the structure of the pixel with a specific structure with a two layer, one the micro bridge, and above the umbrella. The structure is allowed to have a larger micro bridge to allow to capture more light and to increase the distance between the micro bridge and the IC, and to optimize the frequency of the component. Here you can see the breakdown of this component with more expensive with $82. The main difference is the lens and module, more expensive with chalcogenic lens. The die is larger and more expensive. It's the main difference between the two first circuits. The third module, it's from GuideIR. And you can see here the module. The packaging of the module is performed by Ofilm, a specialist for the camera module. And you will find this camera from GuideIR infrared in the small thermal imager from FLIR. You can see the very small module. And for this component is very close to the first you have seen with FLIR, lepton. A small component with a small volume, a low definition. For the technology, it's very standard with ASIC with a microbolometer component, and above a wafer level cap with a window, and you can see here the cavity, the window, and here the microbolometer and the ASIC die. For the side, the characteristic of the die, with you can see the pixel area, the composition pixel around the pixel area, and after all the AOIC part of the circuit. The definition is low, but the pixel is larger than for American company with 17 micrometers for the pixel. That explains that this die is larger than the FLIR component. You can see here a cross section and schematic from the microbolometer structure with the leg, the contact, and the support for the vanadium oxide sensor. And you can see here the the cost. The breakdown cost for this component the cost is either that for FLIR because the die is larger because with their 17 micrometers pixel, and the lens is not in silicon but in chalcogenide material. And the last, it's a Iray T3S module for smartphone. You can see here this module for smartphone with a USB connector, but after it's very different from the another component because they don't have developed a specific component with a low definition, but that used a standard product. You can see in the internet site for this component can be used for security camera, for example, or other application. And that explains a very large component. And for this component, it's they are not developed their wafer level package technology, and they use always a ceramic package with a window here, the ceramic package on the frame, metallic frame. Other part of the system, you have the shutter module and a very large lens. You can see here some detail for the component with a ceramic package, the getter in the package, the die, and the wire bonding to connect the package on the microbolometer die. And the high definition with more 100 to 2000 pixel explain the large die dimension and the large the expensive price for this component. Second parameter, it's pixel pitch. It's always at 17 micrometers, and it's larger than for the American company. You can see here the structure with some different. Here you have two structure with two levels, with one umbrella, and you can see, and the under the microbolometer part. The umbrella kept the thermal data and on all the area of the pixel to optimize the sensibility of the component. You can see for the cost breakdown, the price is very important because the die is very large. You can see here, and after the lens is very large because and in the chalcogenide material. When you have a large die, you need to have a larger lens to create your optical camera. Here, a small comparative between the two, the four camera. You can see the main market, and with the only the Iray camera can be used for industrial or security application. All the other component is very small and with a small definition. They are very developed for smartphone or, for example, drone application, small drone or consumer drone. And generally, this module can be assembled with another optical camera to combine the optical and the thermal imaging data. You can see here the camera dimension, the different definition, the die area with a very large die for the last, and after the dimension, the dimension for the other die, and the different type of material and the material cost. Yes, thank you for your attention.
Thank you very much, Sylvain, for this very interesting presentation. So now let's continue our presentations with Olivier Andrieux from Piseo. So over to you, Olivier.
Yeah, thanks a lot, Iray. So my name is Olivier Andrieux, working in Piseo as innovation technology leader and system architect. Maybe I will start, before to talk about the T3S camera, we'll talk about a bit of Piseo, just to explain why we are interested about this kind of products and topics. So Piseo is an independent innovation center specialized in the design and characterization of illumination, detection and imaging systems, integrating advanced photonic technologies. Our service offer consists in consulting and test lab, and it's supported by many optical simulation tools and photonics laboratory equipment as well. We help companies for all business sector to innovate and optimize their product. Well, in past few months, we have made different studies in the domain of thermal imaging, developing knowledge and competencies, and in parallel, we have considered that the market of thermal imaging and module is growing at a rapid pace. So we have supposed there's a need for users, integrators, and sensor manufacturers to benefit of independent infrared camera or module performance data. So we have decided to realize independent performance analysis that can help to understand technical data sheets and discriminate between marketed products. So the first report that will be presented here today concerns the T3S camera from Iray. But other reports will follow next, and the next one on the list is the boson high resolution, let me say, from FLIR. This report will be available beginning January. We are finalizing it very soon. So then we plan to propose a report on the camera from Guide, and next report will follow all over the year. So the T3S camera from Iray is one of a portfolio of compact thermal camera plugins for smartphones. These cameras address many consumer and industrial applications. They differ in terms of resolution, accuracy. The chosen model has a 17 micrometer pitch volumetric sensor and has been studied by System Plus Consulting. It is given for resolution or NETD of better than 60 millikelvin, and it is also given with temperature measurement accuracy, temperature measurement function, and the related accuracy of ±3%. This camera works with an Android interface when the module is plugged on the USB connector of the smartphone. When using, you can see immediately a thermal image with grid details when the focus is down. The focus is done manually, by the way. The control menu allows many functions. So you can make image capture, video capture. You can activate the shutter. You have the possibility to parameterize or to set the color, specific color mapping. Here, this is a gray scale, and there are 2 gray scale and 4 color maps available. There are also temperature measurement functions. You can see it on the right up on this slide. Which allows to have temperature measured on different points of the scene or area of the scene. This temperature measurement function is associated to temperature parameter settings, which is in the right and down on the slide. But we will talk about that later on. To analyze this camera, we have tried to get images at different steps of internal treatment. That is the image resulting from different steps or process of treatment. The readout IC digitize the pixelated signal from the volumetric sensor. Then there are correction functions applied for eliminate the thermal drift or the non-uniformity of the pixel response. And then there are some image processing in order to adapt the signal to the right color chosen and the level dynamics adapted to shape the image, to have a readable image. So getting the image is made through a specific software that we have developed that support different commands and on which we are able to get a raw image, as you can see on this slide, F, or a corrected image or a final image. So that's the possibility. We have built this possibility to analyze the camera. We have qualified first the performance of the sensor. For that, we have selected different parameters representing the ability to deliver an accurate and stable image. So there is the responsivity, which expresses the sensitivity of the pixels to the radiations. We are talking about the NETD, temporal NETD. Noise equivalent time difference, which express the noise in temperature, the temporal noise, which is expressed in temperature unit, so in millikelvin, for instance. We are talking about the linears and dynamic, which express the maximal temperature range that can be translated into the image. We have also checked the bad or dead pixels that are defined according to their level, their responsivity, and also their NETD. We try to work on pixels that are in the normal, which have a normal response about this criteria. The operability is linked to the bad pixel. It is the number of usable pixels in the sensor. We have also quantified the performance of the non-uniformity correction as well as the residual fixed pattern noise, which is calculated after the non-uniformity correction. We also measure the thermographic function, which show the relation between the pixel signal and the radiated temperature. And also we have got the focal plane temperature of the sensor. The protocols that we applied for measuring these parameters are well defined and stable. You have, as an example, you have the definition, the way to measure the responsivity here, consisting to get 50 consecutive images at one temperature, 50 consecutive images at another temperature of the sun, and making the responsivity matrix by looking at the sensibility of each pixel with temperature. Most of the tests have been done with blackbody, which ensure a stable and uniform temperature send. The surrounding temperature is controlled in a climate chamber that you can see in the picture. Okay, this is, let me say, some explanation about the protocol that we have used. Let's talk about some results now. So the T3S delivers a signal over a 14-bit scale. We have observed less than 10 bad pixels, which are schematized with in the picture down. This reflects, in our mind, the good quality of the volumetric sensor. The NETD is measured between 60 millikelvin and 20 millikelvin, depending on the temperature of the sun, which is fully in line with the specified values of expressed in the datasheet of this camera. And the responsivity of 80 levels over the full 14-bit scale allows a theoretical dynamic of measurement which is below 200 and 250 kelvins. Iray apply, let me talk about the non-uniformity correction and the flat field correction also. Iray apply a 1-point flat field correction to reduce the non-uniformity. And as you can see on this slide, the raw image on the left is completely translated by this correction into a readable image. This is not the final image, by the way. The final image, which is delivered to the screen, is transformed by some tone mapping process and transformed in an 8-bit resolution image. Also, but we talk about on the next slide. When measuring on a black body uniform scene, the applied correction leads to a uniform image with a non-uniformity, which is evaluated to with a standard deviation criterion of some kind of 17 levels on a scale of 14 bits. So it can be appreciated as a good value. However, when P0 apply another correction, a 2-point correction, meaning applying an offset and gain correction for each pixel based on 2 reference temperatures, the resulting non-uniformity is reduced in same condition to 2 or 3 digital levels. So that's that means that the sensor has a very good behavior, and that that's maybe a way to improve the feature of the camera by changing a bit the factory calibration and put it not only an offset gain calibration, but also a 2-point calibration with offset and gain. The flat field correction is the first step of image processing of this camera. In the image processing pipeline, we could get the raw image. This is the image on the left, for instance. We could get corrected in. Sorry, the raw image is not on this slide, but we could get the raw image. We could get the corrected image from non-uniformity and thermal drift. We could also get the final image. We have investigated some details of real image with pretty high dynamics on the scene to understand the steps and the algorithms of the image processing which is applied by on this camera. And we have found this enhancement is based on 3 steps that we have described there. So first step of sharpening. So there is a sharpness increase to amplify the contrast of the edges. Then we have identified an histogram equalization process to improve local contrast and enhance more visible details. Principle there is to distribute the image levels in order to reduce the histogram peaks. And a third step, which is a gamma correction to synchronize the histogram according to the non-linear human perception of the luminance. Then the image is converted into a 8-bit scale. And playing with the parameters and with the strategy of correction, we have got the same or very similar image than the image produced by the camera. So that's our explanation for explaining what are the process, the image process which is embedded in this camera. Let me talk about the temperature, the behavior with temperature. So you have there the thermographic response, which transforms the signal level into temperature. The relation show a 14-bean scale, which cover a same temperature, which is comprised between -20 degrees to 120 degrees, which is exactly the domain which is specified by Iray. And we can see there the behavior at different ambient temperature from 5 degrees to 45 degrees. What is interesting to see there is that this measurement covers the full window range that is specified by Iray, which means that we can have some distortion due to saturation effect in some extreme cases. When I say extreme cases, this is the conjunction of a cold ambient temperature, for instance, associated to hot temperature on the sand, or in the contrary, hot ambient temperature associated to cold temperature of the sand. So in that case, we can have some distortion of the thermographic response and also on the image locally. To complete the view of the temperature, so this camera allows to a function of temperature measurement, which consists to display a temperature value on selected points or specific areas of the scene. This function is nice and easy to be used, but the question that we have is to understand if this measurement is accurate and what is the level of what is the signification of this measured value. So we can make two observations on this point. The first is that the measurement that we have done on the sensor show through the RFPN measurement show some drift that have been measured at 25 degrees ambient and different other temperatures, which can be interpreted or extrapolated to ±3 degrees in taking into account all the temperature range. Well, and it is exactly the claimed value from Iray. The second observation is that there is the possibility to adjust the measured value by adjusting many parameters that are proposed on the screen of the smartphone. So you can see there that you can adjust the humidity, the ambient temperature, the distance, which are quite parameters that are easy to estimate. But also you can control the emissivity, the reflection of the surrounding scene, and finally you can apply a correction of set in the range of ±3 degrees. The more influential parameter is the emissivity, which represents physically it represents the capacity of an object to re-emit energy depending on its temperature. An ideal black body has an emissivity of 1, and a real object has an emissivity which is lower. But the point is that an incorrect setting of this parameter may change the temperature reading by more than, we have made some tests and we can have a deviance of more than 20 degrees. In the case of the FLIR detection, the human skin is usually modelized with a factor which is comprised between 0.94 and 0.98, which is sensitive. This deviation or this variation of the emissivity parameters can lead to deviation on the temperature with the model installed in the camera of 0.5 degrees, which is quite close to, let me say, 10% of 5 degrees range when trying to measuring a FLIR. So, in my opinion, in the context of FLIR people detection, it represents some risk of wrong detection. A first risk can be linked to the variation of the emissivity, the skin emissivity between peoples. And the second risk is linked to to some kind of inappropriate setting of the parameters in the table. By the way, we have to be aware that this table is presented on a small surface. This is the surface of the screen, and can be manipulated by big fingers or by people that have accommodation difficulties, and then can be disturbed. Put 0.90 instead of 98 instead. So some difficulties we can have some difficulties to find the right parameter for having the right temperature. To conclude this evaluation, and regarding the thing from pure optic point of view, we have confirmed, thanks to the evaluation from System Plus, and we have been able to modelize the optical behavior, and we have confirmed the f1 aperture, for instance, which generate a small range where the sharpness is optimal, and this is linked directly to a small depth of field, which obliges the user to make an accommodation very soon, depending on the scene. We have also confirmed some kind of vignetting or distortion effect, but by the way, this is we estimate this is classical with this kind of optical structure, which can be qualified as a cost-effective solution. Our opinion of this T3S camera is that we have very good correspondence between the measured value that we have done and the data sheet claimed by the manufacturer, which is good. We have seen good image with a good quality, thanks to probably to a very good volumetric sensor, and associated to performant three-step tone mapping process. What we have seen also is that the interface, the Android interface, which is called external interface, is user-friendly. It's easy to be manipulated. I would say the drawback of this camera is that there's some sensitive manual focus that must be often realized to reaccommodate depending on the scene. By the way, it's easily possible to disassemble the lens to the sensor, and that can be a risk for having some dust or perturbation on the sensor window. But the main risk that we see using this camera is related to the temperature measurement. There's a large risk of error of temperature measurement if the user has a low background in thermal measuring principle, which is most of the time the case. We have not explored the thermal measurement algorithm, but seems to be very interesting. Well, to finish this presentation, we can say very summarized that this camera is a good value for money products, but requires some improvement to be in a professional use. Okay, thanks a lot for your attention.
Thank you. Thank you very much, Olivier. Thank you for this very interesting presentation. We are now going to conclude this webcast with a Q&A session. We have not too much time, but we will try to answer. And the other question will be answered by email. So we can start, I think it will be with you, Dimitrios. Yes. One question, 12 micromillimeter pitch, still the smallest pitch on the market.
Can you hear me?
Yes, we can hear you well.
Yeah, not micrometer, yeah. So 12 micron pitch is where many players are trying to move into. So because it translates to smaller eventual size for a higher definition sensor and camera eventually. But it's not the smallest pitch in the market. We know that Iray in China has a 10 micron pitch sensor released last year. And of course, many players have R&D in these pixel pits, and we know of one player, cannot say the name, that is at the 8 micrometer R&D. But yeah, there is already a product in the market at 10 micron actually.
Okay, thank you, Dimitrios. One other question, maybe that's a quick question, I guess. Has Ulysse entered into the consumer market or staying only in defense?
This is for me, right? For me?
Yes, for you, Dimitrios. Yeah, I would say.
So Ulysse, yes, Ulysse now called Linred actually after the fusion of the Sofradir and Ulysse companies. But yes, it's already in the consumer market. I don't know if the question is the person that asks the question considers the commercial market or the pure consumer like smartphones or I don't know, everyday objects. I suppose they mean commercial market. So yes, in commercial market, Linred is already there in personal vision systems, for example, or security, surveillance. Not for defense purposes, of course, more perimeter protection. And also recently they're trying to, they have entered the smart building market with some design wins. You can find more info, I think, on the internet on that. So yeah, they're already there. Yeah.
Okay, thank you very much, Dimitrios. Sylvain, one question for you. Do you think that small modules have sufficient performance?
Good question. That's difficult to know. Generally, the smallest module are the system with optical camera. They are not used only for the night vision, for example, but more for measurement, temperature measurement, and for check the motor, the yes, mainly this type of application, and for consumer application, and they are generally that can be combined with optical camera that can be allow to reduce the number of pixels and reduce the cost of the module for very consumer application like a smartphone.
Okay, thank you. Thank you. One question for you, Olivier. How did you retrieve the intermediate image provided by the sensors?
Sorry, do you hear me? Yes.
Yes.
Okay. It is not obvious as we have built some hacking software, let me say, where we have found specific commands to get the properties of the camera based on the SDK, but also based on information that we have got anyway. So we have built for that a specific software which is able to ask to the camera to send appropriate information, which is probably not planned at the beginning. And for instance, the FPA temperature was dissimulated into a package of data that we have analyzed to understand at the end that the parameter that we didn't understand was related to the temperature.
Okay, thank you, Olivier. Another question for you, Olivier. Why is the Iray lens need to be disassembled for packing?
I don't know why the Iray has chosen this option to display the lens, but this is probably for packing constraints. The fact is, when you want to use the camera, you take it, you plug it on the smartphone, and you have the possibility to put the lens and move the lens for finding the right focus. So I guess this is a question of only a question of packing first, and the fact that we need to have this moving turn moving for having the accommodation.
I can explain.
Yes, please.
Generally, for this type of camera, you can purchase different lens for different focus. And if you go in the internet site of the manufacturer, you can purchase the camera with a different focus, different lens.
Okay. Okay, guys, thank you very much for those information. We still have some questions, but time is gone. So the webcast is ending now. We will answer the other question by email. Just to inform you, tomorrow you will receive the link recorded session of the webcast. Also, please feel free to share our presentation with who will benefit from our data and analysis. Finally, please let me remind you that you can find all our market research and turn-down reports, as well as our monitor and tracks on our website, hi-micronews.com. Do not hesitate to contact us if you need additional information. You can find our contact information on the last slide of the presentation. Again, thank you very much for joining us today. Have a good day. Bye-bye.